So today we're going to look at the Kollmorgen Pancake motor. So it's a really thin motor, and the model number I have is the N9M4. I've seen these motors before with tachometers back in the 400 series days. We tuned these up with a filter between the drive and the motor. So we'll take a quick peek at the specification for the motor. You got your ounce inches for peak and continuous torque, 3,000 RPM, max speed 6,000. Normal stuff, 30 volts design voltage for top speeds, 7.6 volts per kRPM, 7.5 amps continuous stall. It's a little bit different than the rated at 25 or 40 degrees C if you use Newton meters divided by the Newton meters per amp. Anyways, the unique characteristic of this motor is the really low inductance. This one says less than 30 microhenries. I think we measured it at around 50 with the tool. It also has some winding resistance. The spec sheet that I got on this motor separately with the motor said less than 100 microhenries. So not sure what less than 100 microhenries is, but it's probably not more than 100 microhenries. So that's going to be kind of a problem for a PWM amplifier in a couple of ways. One thing to be interested in is the ripple current, and this is the worst case ripple current at a 50% duty cycle. You can see an old style drive used to switch from 0 to high voltage. The new drives have center weighted modulation. So the worst case ripple is at twice the switching frequency, which is at 32 kilohertz. So when you're at half voltage across the motor, that's the worst case, half power supply voltage. We could double the switching frequency to get 64 kilohertz if we need to bring the ripple down by increasing the switching frequency. But if you look at the change in the current over this change in time, so that's the classic formula for di dt equals V over L. As the inductance goes down, the change in current goes up. And as the voltage goes up, the change in current goes up. So there's many ways to address this ripple current. You can decrease the bus voltage. I'm going to use 48 volts today, but you could use 24. And increase the inductance. So we'll take a look at that here. But first we'll enter the data for the motor. So got a Kollmorgen, got some inertia, peak and continuous torque. The max speed is 6,000. Newton meters per amp, volts per kRPM. I'm going to say 1 ohm because it's got a couple of numbers here on the data sheet. For resistance, it's got the terminal resistance and the armature resistance. I think, they'll add up. It's the total resistance that we're worried about for the ripple watts lost. And let's take a quick peek at that here too. So I used a 48 volt supply, added up the resistance. I'm going to say 80 microhenry because that's what we measured with the inductance meter. That's a ripple lost watts of 18 watts, which it's not bad. It's a little bit more than 10% of the motor's watts. We could probably do this without inductors, except very low inductance can sometimes cause a short circuit. So if we're less than, say, 50 microhenries, that could be a short, trigger a short. And there's a case when we're trying to control the current with a PWM amplifier. If there's ringing at the time of this, the current measurement, then we could get some funny readings. So I think that's what happened here with this motor. But anyways, we calculated the initial tuning values and looked at the current here. So what I'm going to do is take a look at the runaway condition that occurs without adding some inductors. So what we have here is the Pancake motor. It has a shaft in the back and the front for the load and a typical encoder. We're going to run it today in open loop velocity mode or current mode. You could put a feedback device on the load and close the position loop that way, running this in the back EMF mode. But typically we see an encoder on the shaft of the motor. It's extended out the back for that. And then you could have dual loop with a Copley Plus drive. This is a dual axis AE2, the 9030, so it's a large peak, but it can deliver the 6 amps. It can deliver 15 amps, but this motor only needs 6 or 7 amps. I've got a XP power supply connected to this development kit. I'm using a 48 volt, and these are the SPB inductors that I'm going to use. But we can see that when we're doing the current tuning, we have the commanded and actual current, and with this low inductance, I can't turn the gains up too high. I get oscillations. So this is the quantization noise you see here. Plus, we are able to get to the commanded current without any inductors added. But there it is. So into this runaway condition, the current's all over the place, so we're having difficulty controlling the current. So what I'm going to do is disable the drive, add the inductor. I'll show you these SPB drum core inductors. These are the 150 microhenry inductors that we have in the price list for people to use. The two inductors, drum core, in series with the motor at the output of the drive. Again, this is the DC brush, so it's wire. If you had a 50 microhenry brushless motor, you may want to add inductors too. One advantage of the inductors is the reduction in the noise emission. I don't want you to worry about using a Copley for inductive noise, because Copley's rise times are at least 5 times better than the competition. So now with the added inductance, we can see much better current loop tuning capability, commanded and actuals much better, and there's no runaway condition possible. And just a note, back to the rise time of the Copley, you can see at 100 nanoseconds per division, we've got about 200 nanoseconds of rise time. This is significantly quieter. Had the edge been a 20 nanosecond edge like the competitors, it would produce at least 5 times, and if it's a square law, 25 times more noise in the system. And this would typically be felt over the distribution of the PWM signal from the drive to the motor. You know, got to put the case of the motor to ground, but you still have capacitance between the PWM and the cable, and the coil to the case capacitance. So PWM frequencies, high frequencies, tend to squirt out of these areas here, whereas the Copley is considerably quieter. And of course, we have some inductors here, so you know that will slow the rise time down even more at the output. And this is the poor man's filter, so this is very good for low noise and emissions, especially around very susceptible equipment. And you know, the current loop tuning is good, about 1 kilohertz of current loop bandwidth. And we're looking at the velocity loop tuning here. I've got the commanded velocity, a little above 300 RPM, and the actual velocity. Now, again, there's no feedback device on here like in encoders, so I'm doing this open loop velocity. And of course, this is based on a math model. If we take a look at the back EMF constant of the motor, that's volts per K RPM. If you put 7.6 volts out, you go 1,000 RPM, plus some IR drop in the motor. So at some current, you get some IR drop. So these parameters help tweak the model. What you'll notice is that you'll get about 5% of the DC bus voltage for controllability. So with 48 volts, that's a couple of volts. So a few hundred RPM seems to be fine here. So we're going to take a look at a few speeds in relationship to the PWM signal. So when we're commanding 0 velocity, we can see the motor shaft's not turning, but we do have PWM action. Just looking at the U output, the V output would be exactly the same. So as we go in one direction, one pulse will get smaller while the other one would get bigger. So that would produce the difference between the U and the V, and current would flow. So at a 0 speed, we see the perfect square wave of 16 kilohertz. And if we get a little bit of speed out of the motor, again, we're down at the low end of the controllability, but we still have some voltage mode with IR comp, but not much difference in the pulse width, a slight change. As we increase the speed, speed by varying the pulse width, and try a couple of speeds here. You can see 1,000, 2,000, 3,000. We're starting to develop a considerable amount of voltage to the motor. .6 times 3 to bring you awfully close to the bus voltage limit. Times 3, 22 volts. Plus some IR drop and some PWM limit. The design voltage is 30 volts. Probably get pretty close to 3,000 RPM with 24 volts. Better tested. All right, well, this is Pancake motor, and this is open loop velocity mode. Again, if you had a feedback device on the load and on the motor, you could do dual loop. I'd probably use some integral in the position loop if it's on the load. Otherwise, I'd use the velocity integral for the motor velocity if there's an encoder on the motor shaft. Well, thanks for watching.